Hello everybody, this is Tom and welcome back to my weekly physics explainer video. Today we're going to be going over problem number 18.50, and it asks, a 3-meter long pipe in the figure is closed at the top end. It is slowly pushed straight down into the water until the top end of the pipe is level with the water's surface. What is the length L of the trapped volume of air? So for this one we can use the ideal gas equation, as always, PV equals nRT, and before it is pushed down, we know that the pressure inside the cylinder initially should be about equal to 1 atm, which is just the normal atmospheric pressure, and that's going to be equal to 101,325 pascals. And when it's pushed down, it's going to be a new pressure because the water will start to enter it, and there will be less room for the air, so there will be more pressure. And this can be represented in this equation, P2, which corresponds to the pressure when it is pushed underwater. That's going to just be the initial pressure plus the density times the gravitational constant times this length L, which is right here in the figure. And since we know that R is constant and the temperature is constant because it doesn't change, or at least they don't tell us that it changes, so we can assume that they're probably constant. And we can also know that N is also constant, which is just like the number of moles of air inside of the container. So since we know that all of these are constant, we know that even if we change the volume and pressure, the volume and pressure, the initial volume times the initial pressure will equal the new pressure multiplied by the new volume. So these two volumes are different, but they're just both denoted as V, so keep that in mind. And we know that the volume of a cylinder is just the area times the height. And of course the area is just the area of a circle multiplied by the length of the cylinder. And I essentially just substituted this in for the volume in both of these. I just divided out the area on both sides to get 3, because we know that 3 is the initial length of the pillar of air, and L, because we know that L is the new length of the pillar, or like the cylinder, not the pillar of air inside of the cylinder. And if we rearrange that, we get P2 equals 3P1 over L, and then we can plug that back into this equation to get 3P1 over L equals P1 plus density multiplied by the gravitational constant multiplied by length. So if we do that, we know we can rearrange the equation to try to solve for L right here, because that's what the problem asks us to solve for. And we know that the density of water from a quick Google search is 997 kilograms per meter over meters cubed. We know what the gravitational constant is, 9.81 meters over second squared, and we know what P1 is from our assumption. So we multiply both sides by L to get the second equation, and we subtract the 3P1 over in order to get something that looks similar to a quadratic equation, to something that we can solve with the quadratic equation. So if we use the quadratic equation, we can get L is equal to 2.43 meters, and that will be our solution. Thank you very much.